Thank you all for coming, and this is the back to basics talk, or at least back to what should be basics. The testing, should be the basic thing we do. My name is Fedor Pikus, and from Mentor Graphics, now the Siemens. How many people regularly test their code? How many? Excellent. How many people regularly test their code before they write it? Those who didn't hold their hand, remember it. You may be wrong. We'll get to that. So, in the nutshell, the test-driven development is about writing tests before the code. Thinking backwards, it is. The thing is, you're probably already doing it at least sometimes, but the other part is really, this talk is probably 10% about test-driven development, pure test-driven development. And the rest is about good testing practices and the effect it has on your development process. If you do the remaining 90% and you never do the 10% about doing the test first, you're doing really well. So let's talk about test-driven development. Test-driven development, it's much more than the practice of writing tests first and code later. And that little bit of practice is actually probably the least important bit. It's about the software engineering process and the effect it has on the development. It helps you as a programmer to organize and discipline your thoughts. It's a method for interacting between the teams, for interacting within the team. It's a method for organizing your projects, for setting goals. Overall, it's not so much about what it does to your code. It's about what it does to your mind. The classic test-driven development is a very short development cycle process. You write tests for the new features. Note, I didn't start with you write code. I said you write tests. You run the tests and you expect them to fail because you didn't write the features yet. You write the code, you make the tests pass, you run tests, confirm that they pass, you iterate. I think there is echo in the room. The first time you write the code just to make the test pass. So it's not a very good code. Then you refactor and improve the code, and you make sure that you didn't break any test, and you iterate on that, and then you go back to the beginning to write the next feature. And there are lots of questions here. The most obvious is one, why? And well, we'll answer that during this talk and at the end of the talk, but lots of the practical questions. Write the tests for the new features before the code. Run the tests, expect them to fail. Well, I don't have the code yet, they won't even compile. What do you mean run? Shouldn't we at least declare the interfaces to make sure something compiles? Write the code to make the test pass. Just enough to make the test pass, nothing more? Run tests, confirm that they pass. Okay, well, that's good, the test pass. Did we have enough tests? Refactor, improve the code, run tests, refactor and improve the code, run tests. For how long? Are the tests that we end up at the end, the ones that we use to refactor and run and confirm, are they still the same that the ones we started with? Did we create more tests? Did we create different tests? Not as simple. So since I brought up the subject of did we create more tests or different tests, what sort of different tests can we do? Well, there are unit tests, and that's a test for testing a small bit of code or a logically isolated bit of code. We'll talk more about that in isolation. Integration tests, tests for interacting of several components. System tests for the entire software system. By the way, not consistent terminology here. You may find the word system testing used to mean what I mean integration testing, and you may find the words end-to-end testing used to mean what I call system testing. There is this thing sometimes called point test. Again, there is no established terminology here. It's kind of like a unit test, but you use the rest of the application as a test driver for the program. Basically, you run the entire program or a part of the program, but you carefully select the input data to test one small chunk of your code. Acceptance tests. This verifies that you pass certain requirements. Regression tests tracks for changes where you don't expect them. Performance tests can be any of the above. You tracking performance of your code. Performance is as much of a goal. I'm not talking about benchmarking. I'm talking actually about you have a performance requirement. It could be as much of a goal as a correctness requirement. This code must produce correct result and must run this in this time. And these are your requirements. Both need to be tested. Now, it's important to know the difference. In reality, one of the most common reasons for basically abandoning your test suite and not giving up on it is trying to use the wrong kind of test for the wrong purpose. So for example, if you start using unit tests as system integration tests, you will probably in the long run will be unhappy with the results. It will be unstable, it will be too hard to maintain. It's very easy to start doing this and it's very hard to keep going. Unit testing, we'll talk about it because it's most commonly used with test-driven development, and it's probably the most misunderstood kind of testing, but it's also the kind of testing that you as a developer should run. The rest is split between the developers and QA. Unit testing is on the developers. It's testing of a unit of the code outside of the rest of the program. What's a unit of the code? Very often people think it's a small thing, it's like a class. Well, in object-oriented programming, classes are usually units, but not necessarily units are classes. Units could be large. At some point, your entire, let's say you're writing a database. Your entire database could be a unit for some set of unit tests. Now, it's built from other units, and the assumption is you have already tested those. So now, the database is a unit, and you're testing its interfaces as a unit, basically as a black box. So usually they're small, they could be large. The important thing about unit testing is it's done without the rest of the program. So where do we get like main? It's actually written for each test individually. You can do it by hand, it's hard. You probably will not continue your testing for long if you do it, but there are unit testing frameworks that basically automate the entire process for you. Okay, so that's where the rest of the program comes in, but the rest of the program isn't just the main. You also have to put your classes, your units in the correct internal state, which normally the rest of the program supplies that state for you. In a unit testing, you basically fake it, or you synthesize it, you generate it. Sometimes it's easy, sometimes it's very hard. We'll talk about some of the techniques to do that. Throughout the talk, we'll be using this example. I want to write a solver for the Sudoku puzzle. It's not particularly hard, easy to show, that's why I'm going to show some of it. Everybody knows what the Sudoku puzzles are, right? You get the square, 9 by 9, there are some digits in it. You have to fill the rest of the digits. The rules are every row, every column, and every little 3 by 3 square must contain all 9 digits. So no repetitions in any column, in any row, in any square. So this is how the filled one looks like. If you look through every column, every row, every square, you'll find there are 1 through 9, one of each. Well, before you can write the solver, you have to actually write something that represents the puzzle itself, so you know where the state is. You'll probably write the puzzle itself as a class, and you need a get to access the value of a particular cell, and you need the set to write the value into the cell. You could get fancy with operator square brackets, but this isn't unreasonable. Okay, I'll show you a Google test framework. There are other unit test frameworks. Fundamentally, they're all very similar. Names change. The idea is the same. You include your code you want to test. You include the test framework, and then you do the test. Test has a name in the Google test test, they let you group the test by group, so group name, test name, doesn't matter. And inside of the curly braces, inside of the, where's my pointer? Inside of the curly braces here, that's your code. That's what you're testing. So this is the actual code you're testing. First thing you do with any unit is you construct it. That's really is the, like, pretty much if your unit is a class, the first thing you do in a unit test, you just test if you can create it. Everything else comes later. Okay, I created it. Now I want to run some tests on it. In the Google test syntax, it's expect. In CXX units, it's assert. Doesn't matter, whatever your framework is, they have something like this. This is the call I'm going to make. This is the result I expect to get. If I don't get it, it'll tell me. So I expect that the constructed puzzle is empty. I'm going to check that it is. Now, this is actually the complete file. This is it. No main, provided by the framework. Okay, you build up unit tests. The one important thing about unit tests, you build up the next test on top of the previous one. So here is the next test. I construct it, and I'm going to test that I can set a number in the cell. The important part here, I don't test that what I constructed is still empty. I trust my previous unit test. This is important in unit testing, otherwise you'll never get anywhere if you keep just building up your unit test. You trust the previous test. So this test is for the new feature only. The previous test was just for the constructor. Okay, we got the constructor, it works. This test is just for the set. And yeah, it should be bigger than that. It doesn't fit on the slide. Now, here is an interesting bit. Let's say, what should happen if I try to set a cell that doesn't exist, out of range? Well, what should happen depends on what my documentation, what my specification says what should happen. Let's say I specify that it's an error, and I should throw an exception. Well, I should test for that. This is very important. All aspects of documented behavior should be tested, including things like errors. If you have specified behavior on error, you test that that's how the behavior is. Test-driven development most often uses this kind of tests. Why? Well, test-driven development is about fast, short cycle incremental development. Unit tests are ideal for short cycle incremental developments. One reason is, in a test-driven development, you start testing before you write the program. So you really probably don't have a main. You don't have the rest of the program. You may not have the inputs. You can't create your state of the program. You start to write your program from somewhere. Wherever you started from, you don't have the rest. How are you going to even run that code if you don't have the rest of the program? Well, that's where unit tests come in. There is no rule that unit tests are the only tests that are used in test-driven development. You can do test-driven development with integration tests, and you often need to do it, but most common. Let's look at the test-driven development process. As I said, very short development cycle. But we had all these questions about what it means. And we had questions for pretty much every step of the process, so let's go through them. When do you really write the unit tests? Okay, of all the people who do it, or who want to do it, or who think that ideally they should be doing it if they have enough time, should you write the test before the code is written at all? After the code is declared, but before it's implemented. So when the interfaces are declared. When the interfaces are declared and some dummy implementation is provided so it will at least link. Okay, well, the answer is you can do it in any of those ways. They all have some advantages and disadvantages. If you do it before any code is written, your test won't compile. On the other hand, and that's a drawback because your tests may have bugs. That's kind of disheartening thing about code. You know, your tests are code, they can have bugs. Your compilers are code, they can have bugs. Your debuggers are code. You see where that's going. But we do the best we can. So on the advantages, your tests are at this point kind of their conceptual compilation. You compile them in your head. But they describe you how the client code would look like. And in a way, they specify the requirements on the interface in C++ instead of English, because if you write the code, so if I write a set of 0, 0, it means my class must have a method set that takes 2 integers. So it makes me think in terms of the client code before I started designing my interfaces. That's actually a big advantage. We'll return to it later. Also, kind of a note to self here, if my test can specify the interface, could I use them instead of the specification? Well, let's think about that later. If the interfaces are declared, but implementation is not written, your test will compile, but they will not link. The fact that they compile is an advantage. You can verify that your interfaces have been written correctly. They won't link, so you can't do much else. So you go back to basically, it's still a mock-up for your client code, so you do get that benefit. You can write dumb implementation first. Your tests will compile, and they will run, and we expect them to fail, because it's a dumb implementation. It doesn't do what we want. And it's a good thing. It has a benefit because it verifies whether your tests are sensitive enough to at least detect the presence of the code. If your tests work out the same way, whether the code is there or not, they probably aren't testing much. But of course, you don't have the client code mock-up, so you have to write the interfaces to some other form of specification. And the problem with that is you can't overly rely on the expectation that the test will fail. You would like them all to fail, because you really don't want the tests that always pass, even when you don't have the code to test. But even the broken clock is right twice a day. So here is some function that just adds 2 numbers. We have to return something. I mean, it has to return an integer. Well, that integer could be something you test for. The most common way, in my experience, is writing the tests after the dumb implementation so you can verify that at least your code compiles and links. If you do it the first way, it's not my term, so some other people invented it. Sometimes it's called example-driven design. And that's basically the value here. You're designing your software, think, okay, if I did my interfaces this way, how would the client code look like? Would I be able to do what I need to do? You're not compiling the tests except in your head, but if you discover that with the interfaces you have in mind, you actually cannot write the test for what you want, you just found that your design doesn't do what you would like it to do before you wrote any code. As I said, the biggest impact of test-driven development is not on your code, it's on you, on your mind. Okay, what do they mean when they say write enough code to make the test pass? Well, here is our function add. This time it adds 4 numbers. And we add 1, 2, 3, 4, expect 10. Is this the valid implementation? Probably not. That's usually not what they mean when they say make the test pass. What they mean is don't do that. Don't optimize, don't put multi-threading in, don't do parallelism yet, don't do exotic algorithms, don't vectorize, don't do any of those things yet. But yeah, it probably should return the results not just for the test, but according to the more general spec that you have. If it should add, if the spec says it should add, it should add. You run your tests, you want to make sure that they pass after you actually implement the code. Well, how do you know when you have enough tests? The truth is, it's always a judgment call. It's always a judgment call. You never have full coverage. You can test even the simplest operation, and you test for these inputs and the other inputs and many, many more inputs, and you can't trust even that. So you will never have proof positive that your program is correct. We have to have some trust that some things just work. In particular, your hardware instructions, you usually expect them to actually just work. So you write for one or few tests for what you consider normal case, you write the tests for all corner cases. It's really a judgment call. You will never have complete coverage. if your judgment was wrong, you will sooner or later discover it, you will have some bugs, and so your tests tend to grow. What's a special case? What's a normal case? Well, you have a benefit. It's a white box testing. You have a benefit of knowledge. So for example, for our Sudoku puzzle, well, setting the value of 5 or the value of 3, it's all the same. There is, it's an assignment of some integer. No value is special. So you probably don't need to test every value, at least every valid value. You may need to test multiple cells. You can automate. For something like Sudoku puzzle, you can do all 9 by 9 cells. You can automate it. For a bigger program, you can't have complete coverage. You need to be careful here. You need to resist temptation to overtest. In real life, one of the most common reasons for basically abandoning your test or not using it as often as you should is tests take too long to run. I need to check in my code. It takes half an hour to run my acceptance test suite. It's at the end of the day, I need to go home. I'm going to check in my code. I mean, that's really just how it is. It shouldn't be, but it is. It's a test that never, very good tests that never run are still not as good as partial coverage that gets run every time. As a developer, you know what the special cases are. So general case, you may, corner case, the corner cell, maybe a special case, it's the last cell in the array, maybe special. So you know what the special cases are for your code. Don't confuse special cases with error cases. So the last line here is not like the other ones. It's actually a normal case for error handling. So don't confuse special cases with error handling. They're two different things, you test them separately. Error handling is a separate function and probably tested in a separate step because your first step is write enough code for the normal things to pass. Your second step is now protect yourself against the errors. And maybe if you have many errors, more than one step. Okay, how long do you refactor? Depends what you refactor for, it's always a judgment call. You may need to optimize and refactor for optimization. You may need to reorganize so your code is ready for the next coding step, the next feature. If you do that, never mix new development and reorganization. That's important. If you need to make some changes to your code so you can add a feature, you make changes to your code that are no first. You finish them, you run the tests, make sure nothing changes, you check them in. Then you make the changes that actually change the results. And the code improvement may itself be guided by tests. You will be adding more tests at this point. The very important, very tricky part is testing really means observing something. So what can you observe, what can you test? We've seen so far everything, all our short examples, but they're actually realistic examples. We tested for user observable behavior. We used public APIs to test. That's also what happens if you do, that's not just unit tests. You do system end-to-end tests, whole system tests. You run the program, you look at the results, that's again user observable behavior. If you have class hierarchies, you can inherit and you can hook up to protected APIs. What else? Well, okay, let's look at this example. This is ugly sort, it's insertion sort, it doesn't matter. Here is the sort. Okay, we're going to run the test for the sort. Okay, here is our test. We're going to run it on an array. The way it's written, it hooks up to a container, and it uses indices. So not an iterate arranged container sort. Okay, so here is some array. We sort it, and we verify that the results are sorted. We can test for all the special cases, sorted sequence, reverse sorted sequence, duplicates, and everything is correct. Now, we still actually, in all of this, we're actually still testing one special case. And that special case is, it's not in the data. It's in the container. The special case is, our container is an array. Data is generic. Input is not. Well, okay. We can do the other container. Let's do the vector. Same vector, so vector with the same data, we can test the results. Okay, let's see. There is that insertion sort. I wrote my own test driver just to not kind of pollute things with the Google test macros. So I'm testing it on the container, which container is an array, and I'll test the same thing on the vector. That was unexpected. Let's try to, oh, okay. What's the difference? Okay, this flag, this compiler flag causes problems. Never use that. Yeah, use that. Okay, what it really does is it's a debug option for STL. So yeah, always use that. What happens here is the insertion sort has an out-of-bound access, which you don't normally detect on an array unless you get lucky and it will crash. You don't detect on the normal STL, again, unless you get lucky it crashes, but debug STL detects it every time. So if you didn't detect that, the sort is actually correct. I mean, it has out-of-bound access, but it will probably return correct results, usually. I mean, you never know what will happen. It's undefined behavior, but most of the time, it will give you correct results. As we've seen in our example, I ran it, and if it didn't crash, it returned correct results. So the problem here is that observable behavior through the public API isn't sensitive enough to test for all the things you want to test. The same thing for our Sudoku puzzle. It probably has an array like this inside. How would you detect out-of-bound accesses if they don't crash and don't lead to incorrect results? Which boils down to, okay, I tested the interfaces, should I also be testing implementation? Well, on one hand, yes, because there are a lot of errors that cannot be observed through public API. The problem with that is it makes your tests very fragile. Implementation changes, implementation is fluid. Sometimes implementation actually doesn't produce stable results, like you may have concurrency, your internal results are in flux. Your final results are always correct, always the same. You can verify them, but what's going on inside is a lot more fluid. Again, one of the most common reasons for abandoning a set of tests is the need to keep constantly updating the test to keep up with implementation or other flaky details, fluid details that you decided to test for. So sometimes you have to test for implementation, but it's as a last resort when everything else fails. Everything else is a lot of things, which means we have other options. But what are the other options? So let's go back to the problem we just had. We had an out-of-bound access on the container that wasn't visible through the public API. Well, it actually was visible through the public API, just not the public API we were testing. It's still an invalid use of the API, but it's an API of the container, not the API of the class that we were testing. And that observation suggests that in addition to testing the interfaces of the unit that you're testing, you should also be testing from the inside. You should be testing that that unit makes valid use of the interfaces it is accessing. Now, if you think of it in these terms, not only the unit should abide by the contracts, but the unit should not violate any contracts that it depends on. You can often remove the need to test for implementation if you just test for the compliance with the APIs, with the contracts, that part is actually public, that part is stable, it doesn't depend on the implementation. Whatever your implementation of the sort is, you should never access the container out of bound. How do you test for these internal contracts? External ones are easy. We have our special testing main, we call our interfaces unit or whatever, and we test for the results. Internal code, well, it's compiled in, and the stuff that's compiled in wasn't built for testing. So we need somehow to substitute the dependencies, the lower level components. Those substitutes are called the test doubles, so most of the rest of the talk will be about this test doubles. They're kind of like body doubles in the movies. Take role of the real thing and have some additional capabilities that the real thing doesn't. So test doubles. Test doubles are usually used for testing the code from the inside. You verify that the code you're testing makes valid use of all the code that it depends on, which is just as important as that the code you're testing lets you make valid use of itself. There are other applications. Maybe you don't have the dependencies yet. Well, array, of course you have the array. I might want to test the Sudoku solver before I actually write the Sudoku puzzle class, so I may have a fake puzzle. Probably isn't worth it in this case. But testing, let's say, communication to the database before you write the real database may very well be worth it. Fake database. The other big thing that the test doubles do is they simplify creating the desired state for the testing. Sorting the container, that was easy. I want to sort the records in the database. So here is my huge database, the server, the backup server, the redundancy, the communication, the backup, lots of other stuff, and all I care about is getting the records and sorting them. Well, I just need an array of the records and the interface to get the records in and out. I don't care where they come from. Maybe I haven't written the redundant server and the backup server yet. I can fake the database. My sort doesn't know any different. Different kinds of test doubles. Test stubs, they're dumb implementations, fakes, simplified, more or less real implementation, mocks. Mocks are an interesting ones. They're test implementations that do internal checking, so they validate or track or verify the calls that are made to them. So our debug STL was a mock because it did all the things that we expected from the STL, but it also validated the incoming calls, the index operator. So there is, by the way, again, inconsistent terminology here. Sometimes fakes is used to mean all of that stuff. So be careful with the terminology when you see it. The line between stubs and fakes isn't always clear. Some people are strict about this. Hard-coded, return 1, that's a stub. Take some value from the input and return that, that's not a stub. Some people call that a stub as well. So fakes are simplified implementations. How simplified? Now, mocks, on the other hand, have that clear differential. They track something in addition. So they do additional inspection on the data that they're called with. So here is a stub, here's a double for a random, for rand. Returns 1, well, it's a random number, why not? But it also counts how many times you called it. So it's both a stub and a mock. Stubs are basically hard-coded things. Just return the value, make your code, compile, link, and run with some set of values that you know what they are. You get control over the data this way. It's valuable for testing. You know exactly what you're testing on. Sometimes you get kind of a more complex stub. You feed the data into it, and then you get it back out. Some people would call it a fake. Doesn't matter. In general, fakes are simplified implementations. By the way, remember in the test-driven development, you write as simple code as you can for the first implementation just to pass the test. Very often that becomes your fake later. If that implementation actually evolves into something much more complex, that could be a fake. So we have a database, we have a backend, redundant, distributed, concurrent with backup and so on, high availability, and we want to test the interface for getting records. Well, fake backend, just a set of records, good enough. Has the same interface, works. Now here comes the problem. Okay, well, before we get to the problem, okay. So here is my sort for, that's my insertion sort. With the insertion sort, I get that container. I can test, for example, for an out-of-bound indexing. I can give it a special container. I can use debug.stl. I can give it a special container that I instrumented to test for out-of-bound access, but I can do other things. For example, I can check that every element was inspected. Just because I got sorted results out of it doesn't mean that it always works. Maybe my input wasn't general enough. It just so happens that the last element in my input was the largest. And my sort has a bug, it never looks at the last element. Well, this wouldn't catch every bug, but if you didn't look at some of the elements in the sorted container, you can't possibly be correct in all cases. So I'm not saying that this is a good test. This is again, an illustration for a simple case, but basically that's the idea. You can inspect the incoming calls on your dependencies. And you can validate that some properties that should be true are true. Like for sort, you inspect it at least once every value. Well, how do you get that test double into your code to play the role of the real code? For our sort, it was easy. The sort is written to take any container. So if I have my guarded, instrumented, observing vector, I send it in instead of the real vector and everything is fine. Well, here's my database. It has a data member backend. And it's written exactly like that. I have my fake backend class, different type. How do I get it in? Two ways. Well, fundamentally one way, magic. Two sources of magic. You know, arcane and divine, sorry. Compile magic and C++ magic. Compiler magic, basically, you make the compiler swizzle in some different code. We've seen an example of it. Debug.stl is exactly that. You turn on a pound define, pound defines make the headers change, a different version of STL is compiled in. Usually it's pound define, you can do some other compiler stuff, compiler flags. Build magic is another option. You change the include path, you change the library path, different version of source code gets brought into the build. You have to recompile everything, of course, but you compile with the code you're testing doesn't change. It's written the same way, but the code it depends on, suddenly it's a different source file or a different object file. And if you think, ew, at this point, consider that if you used any kind of memory checker, you probably use this, because most of them, what they do is they slide in an alternative libc implementation that has a tracking malloc. Well, compiler magic, okay, kind of, easy to do, some uneasy feeling there. Let's talk about C++ magic. So dependency injection. The goal here is to trick your code into using the test double instead of the real code that your testing code depends on. It's actually a particular case of a very general pattern that's called inversion of control. Normally, so you have a class, it has data members. The class control what the data members are, how they're initialized, that's a normal control. If you invert that control, if the injector, the outside code, controls what the data members are and how they're initialized, that's inversion of control. More general than just the testing. If you start using it for the testing, you may discover that you actually like this as a design pattern in some cases. You may end up using it for other reasons. So, two problems with dependency injection. Problem number one, our real data, the one we want to replace with a test double, has a fixed type in the code. It's written in, it's hard-coded, it's back-end right there. Well, our test double is a different type, three ways. Keep the code as written, change what it means. That was the build magic. Keep the code as written, but make the type change at runtime, runtime polymorphism. That's dependency injection. That backend, that BA-END, that's actually not a type. It's a template parameter, also dependency injection. So two ways to do this. Now, in both cases, what's important is this doesn't just happen. You can't graft it on after the fact. You have to design your code to be testable. You have to think about how you're going to test your dependencies during the design. Code must be written to be testable if you want to use these techniques. That's actually a good thing. Problem number 2, okay, I got the types down somehow. Now, in addition to just changing the type, I also must give the class that I'm testing my specific test double instance, which isn't the instance it normally would get. Sometimes it's not a problem. If you have, for example, if you decided to use a template and your database default constructs the backend, it will default construct the different type of the backend. Sometimes you give the instance anyway. To the sort, I give it the instance of the container. So I already give it the instance. If normally you didn't give it the instance, you now have a problem. You have to pass in the instance into the code, which normally didn't take the instance because it didn't expect that it would need it. In the normal conditions, in the non-testing conditions, I expect certain backend and I know how to create it. This is always the issue if you decide to use, 20, thank you. This is always the issue if you decide to use runtime polymorphism, because if you decide to use runtime polymorphism, then this backend is the base class. If you decide, if at runtime you want an instance of a different instance, somebody else who knows what the real type should be just for testing has to construct that instance, and then somehow it has to get in. 3 ways to do dependency injection again. Constructor injection. The instance of the test double is passed to the constructor. Well, 2.5 ways, let's say. Interface injection. The instance is given through the interface other than the constructor. Particular case of interface injection called set injection. The instance is given through the interface other than the constructor, and you have setters and getters. Constructor injection. You create the dependency objects outside of the main class. You create them first. The interesting thing here is the class doesn't actually have the full knowledge of its own dependencies anymore, just the contract, just the interfaces. That's what inversion of control means. Your class doesn't fully control its own data members, just has expectations on them. This is what you normally do for polymorphic, if you use polymorphic test doubles. Database takes a backend interface, which could be any backend, testing backend, real backend, as long as it has the right interface. You can also do it with template types, of course. Now, why would you do it with template types? With template types, you can just construct it in the object, knowing the type. Well, that's true if you're constructing it with the same arguments. Maybe my testing double needs additional arguments. Then I still have, even though the type has been changed by instantiating the template differently, I still need to pass the specific instance of the test double. So it has the additional arguments that the database doesn't know about. The biggest problem with this, well, one problem is general. Yeah, you have to write the code to be testable. Once you start writing the code to be testable, you run into the second problem. More and more and more constructor arguments. And the solution to that is actually redesign. And it's not a bad redesign. Basically, let's say you have a class and it has like 20 data members. You don't pass 20 arguments to the constructor. You restructure your class to depend on 2 components. And you pass two arguments to the constructor. These 2 components have, let's say, 10 data members each, 10 of the original data members each. Again, they have 2 or 3 components each, so you kind of build a hierarchy of these data members by grouping them into logical components. It's actually not a bad thing if it forces you to design this way. It increases the modularity of your design. It makes the design harder. It makes you think about more things during the design. But usually the design is better at the end if you think about how you're going to test the code. It's definitely going to be more testable, but it gives you usually some side benefits as well. And the truth is, the code that is not organized for testing usually does not get tested. It's really hard to graft testability onto an existing design after the fact. Interface injection, fundamentally similar, only the constructor does whatever it does, which may be nothing. Sometimes, so the constructor may not create the dependencies at all, and you push them in later to the interface, or the constructor creates the default dependencies, the production dependencies, and you somehow swap in the test doubles after the fact. It all works. if the injection methods are only used for testing, it's a test-only interface. If you actually decide to design with inversion of control, then that becomes your primary interface. That's how you injector code gives the inverted control to the to the former owner of the dependencies, who is now not an owner anymore, just a client. So dependency injection, in practice, difficult. I mean, ideas are simple. Implementation is hard. The reason implementation is hard is because if you didn't design for this, it's very hard to graft it on. If you did design for it, then it's pretty easy. Runtime polymorphism, has the runtime overhead. The other downside of the runtime polymorphism is it restricts your interfaces. So, for example, let's say you had a function that returns std optional, and now you want to use a test double for that thing that it returns. Well, polymorphic classes don't go into std optional easily. So you probably can't use runtime polymorphism with that interface. And it's probably not the reason to redesign your interface. If you wanted std optional, you probably should use std optional. You just should do something else for the test doubles, make it a template parameter. Okay, briefly, when we talked about writing tests, if I write the tests first, before any code, they do kind of specify what I want to do. So, can I use tests as a specification? Well, on one hand, yes. See, very easy, it's a self-verifying specification. Very easy to check if you comply with the specification. I call f of 1, I expect 3, I got back 2, very unambiguous. You know, you can't possibly miss the fact that you're not in spec. You can't misinterpret the results. The problem is that, again, your tests are never complete. Your tests always require inference. So f of 1 is 3, f of 2 is 5, 7. What's the next one? What's the next one? Anyone? Sorry? 11. I was actually thinking of 9, but yeah, you could be right. So here is the case where inference is ambiguous. I could be thinking of primes, or I could be thinking of just odd numbers. So now this is a trivial case, but inference is very often ambiguous. Now, in reality, there's actually not one question, but two. Can you use the test to fully specify behavior? We already know the answer, not really. Can you use the test to fully specify the API? Well, also not really, but a little closer. So, f of 1 should compile. That's bigger, that's kind of more complete knowledge than f of 1 should return 3. If f of 1 compiles, f of 2 will probably also compile. But it doesn't tell us like how big this int is, or maybe it's not an int at all, could be double. Doesn't say what the return type is. For templates, of course, it's even more ambiguous. So overall, not a good specification, very good complement to the specification. Examples for the specification, illustration of the specification. Documentation, kind of same thing. You can use tests to document the behavior. You get the equivalent of this stupid comment. This code adds X and Y. Yeah, of course it adds X and Y. And this is, if you use the test as a documentation, that's exactly what it tells you. It adds X and Y. Doesn't tell you why, which is what the comment should really do. So, not a good specification by itself, not a good documentation by itself, excellent appendix, excellent illustration, very good for documenting special cases, corner cases. Because for corner cases, that's often what you say in your specification. And f of x returns this and this and this, except f of 0, which always does, like throws. Okay, f of 0 throws. A test for this is perfect. That's it, that's your spec. Very briefly, testing parallel programs. You can do test-driven development of multi-threaded programs. The way you do it is you test each single threaded component to make sure it's correct. You develop synchronization constructs, you test those. and then you start adding concurrency. It's hard to add concurrency a little bit at a time. It's also very important that even though you say test single-threaded components, it doesn't mean that you design your code with a single-threaded mindset and then add concurrency after the fact. Design should be with the concurrency in mind from the beginning if you want to do concurrency. Testing should be first for all single-threaded components. It's very hard to add concurrency incrementally. The easiest way to both test for it and actually develop for it is you build your code from thread-safe components, and you test those components as units for both single-threaded and multi-threaded behavior. And then you do integration testing on the entire thing. So here is our database. It has a transaction queue. It has a log, and everything is in the open, and we just manually synchronize. The design style is known as the big mess. What you want is a thread-safe transaction queue that encapsulates the thread safety aspects. And it should provide you with atomic transaction. By atomic, I don't mean log-free like C++ atomics. It could be using logs inside. I mean the interface is atomic. Every call is an atomic transaction, does some complete transaction operation, is uninterruptible. It happens, it cannot be interfered with. You could use a log to ensure that. Okay, let's skip the interfaces for time. So how do you test concurrent programs? The most common answer is with integration testing. You do unit testing on single-threaded components, you do integration testing on multi-threaded components. That is not entirely, that's not the only thing you can do. Sometimes people say that's on integration, people say concurrent testing is by definition integration testing. That's not true. And the downside is live testing of concurrent programs is always probabilistic. And the flaky tests usually get ignored. You can do unit testing of concurrent programs. What you can do is you test for certain invariants. For example, every time the queue is accessed, this mutex must be hold. That's a single-threaded environment. The calling thread must hold the mutex before it accesses the queue. Then nobody else will be able. If that's true, then you have a guarantee that nobody else will be able to access the queue because another thread can't get the mutex. You don't need to test for the other part of it to make sure that another thread doesn't access the queue because you already tested that any thread that accesses the queue holds the mutex. It guarantees that you cannot have an access by another thread that doesn't hold the mutex. Unfortunately, in order to test for this, for the single-threaded invariant, so this is a kind of unit testing. You don't test for race conditions, you test for single-threaded invariants. Unfortunately, you have to do dependency injection on everything, including the logs. I mean, who on earth would write their code from the beginning with injectable mutexes? If you didn't think about it up front, like, I don't know anyone who does it, honestly. And then you think it through, you get to this point, and now, oh, damn. I need to know, I need to injectable mutex because I need to track it. I need to know if it was taken or not. I need a mock mutex, and a mock queue. Well, mock queue, you might think about mock queue, but my mock queue needs to ask my mock mutex, have you been logged? So you have to dependency inject everything. If you didn't design for it, honestly, you're not going to be able to refactor for it. It's too hard. If you design for it, well, you may be able to. If you didn't design for it or it's too hard to design for it, you go back to magic. So yeah, dependency injection, you have to rewrite all the classes, make it injectable. Not going to happen. It would be nice, but no. We're going back to compiler magic. We've already seen the compiler magic. I didn't inject a new vector, I just tricked STL into injecting a new vector for me because I had the pound define. There is another way to do similar thing, and that is to use the sanitizers. And that's the last idea that I want to leave you with. Combining testing and sanitizers is a very powerful combination. What are the sanitizers? These are the tools that somehow instrument the code or the runtime or both and detect certain errors. So they could be compiler. They could be things built in the compiler, they could replace system libraries, they could be tools that basically monitor your program and intercept hardware instructions. There are different types. So these are three ones that most common ones built into the compiler. Address sanitizer, thread sanitizer, undefined behavior sanitizer. These are all built into like Clang GCC. They don't test for everything. But what they do test for, you basically get an equivalent of the dependency injection on your entire program done for you by the compiler or the sanitizer, and it's much more reliable than just hoping that invalid actions will cause a failure. For example, the thread sanitizer will detect potential race conditions, not just real race conditions. Address sanitizer will detect out-of-bound accesses even when nothing bad happened. You write an out of bounds of the array, there was nothing there, you didn't corrupt any memory, your results will be correct. Address sanitizer will let you know. That same code without the pound define, but with the address sanitizer, out of bound error. So this was, I turned off the debug STL, I turned on the address sanitizer. Now it gives me the out of bound error on the array, by the way, which debug STL, of course, couldn't do because built-in array, there's no debug built-in array. But this thing gave me an out-of-bound error even on the built-in array. So it's a very powerful combination because it gives you a kind of blanket, wholesale, shotgun, limited dependency injection. Limited, you can't sanitize for everything, but what you can sanitize for, very powerful. Underused, in my opinion. People don't think about it often enough. Go straight for dependency injection, or what they can't inject, they don't test. Remember to think about available sanitizers. It's a lot easier to sanitize your unit tests and interpret results than it is to sanitize your whole program. TSAN may not be able, honestly, to sanitize your entire program. It gives false positives. It may be too hard. Getting a TSAN error on the unit test or a small integration test, that's just a joy. You get 10 lines of code, TSAN error right here, how hard can it be? One slide on efficiency. Performance could be a design goal. I'm not going to talk about it, but it could be a design goal, and if it is, you need tests for performance. It's not benchmarking, it's tests for achieving the necessary performance. So, the bottom line, 2 slides. Why would you be not testing your code? Common reasons or things not to do. Flaky tests, flake testing environment, tests that take too long, tests that too much dependent on some internal detail that changes often, needs to be updated too often. Tests that are too hard to maintain. The design wasn't meant to be testable, too hard to test. You can't access the things that you really need to observe to test. Again, the design wasn't done for testing. So these are the things that either make you not do the test to begin with or start doing the test and then give up on them. The later part is more dangerous, more pernicious, because you don't see it coming and then over time you just gradually give up on your testing. Okay, those are don't do's. What do you do? The biggest thing, think about testability from the beginning when you do the design. That's the most important. Dependency injection is a subset of it. Making this observable what needs to be observable. Even if you don't plan to do the test-driven development, figure out this development process, learn about it, think in these terms even if you don't write the test before the code. Think about how the test would look like before doing the API development. That's the example-driven design. It makes you think, okay, if I do design in the way I think I'm about to do it, would it actually be useful? Otherwise, you do the design, and then you discover, oh, it doesn't do what I want. You start ugly workarounds, grafting some junk onto it. You could have avoided it if you just imagined the client code in your head or just wrote it down. Wouldn't compile, wouldn't be complete code, but just, okay, write it down, see how it would look like. If you have this, if you notice that your testing discipline starts to decay, fix those problems as early as possible. If you have one flaky test in your test suite, and you can't fix it now, honestly, turn it off. It's better than people mistrusting your entire test suite. Oh, this test run always fails. We just ignore the results because you run the test and it says 1 or more tests fail. It always does that. We just never look at this. Turn off that flaky test. I mean, fix it ideally, but if you can't, turn it off so when it comes back with your test run comes back with a failure, you know there is a problem. Any testing practice that you do follow, make sure to take full advantage of it. If you have regression tests, convert them into the refactoring test suite. If you have acceptance tests, run them with a sanitizer. You're not guaranteed to get everything, but take full advantage of what you're already doing. You may get more than you're getting now, basically for free. And the last thing is, be practical. You write the test, somebody comes and says, oh, this won't find all the bugs. No, it won't. But it may find some. Don't try to figure out what all the bugs are. Do what you can. Thanks.